Okay, here we've got quite a rudimentary, a very simple velocity time graph, and it's just going to help us derive a formula that helps us relate velocity and displacement, or distance covered in a certain direction. So here on the y-axis, it's up and down, we've got velocity, and here we've got time. And you can see something special. This graph doesn't start from 0 and go upwards, it also includes the negatives. Why? Because with velocity you could be moving backwards. You're not only moving forwards, you could be moving backwards, you could be moving forwards. But that's not what I want to focus on today. I want to really focus on the relationship between displacement and this velocity time graph. So the key point for this is that displacement, which is not clearly shown on this graph, is actually just the area underneath there. If I draw a line that closes up that, the area underneath will be the displacement that the object has covered. So this object starts out at time 0, it's already at a speed of 5. You may wonder, how would that have happened? How could it be at a speed of 5 at the start? Well, maybe the person who's drawing the graph is standing right around the corner somewhere there, and there's a car coming like this, and so when they see it for the first time, it's there, it's already moving at 5 meters per second. Maybe it already started moving, and so the first time this person sees it and starts to make a record, it's already moving at 5 meters per second. That could be why. So as the person watches, the speed of this car increases. After some time it goes to 10, then a little later it's at 15. There you can see that the velocity is at 15. You can draw a line to see, right? It's close to 15, and it's at 15 after 2 seconds. If I extended this line to something like that, all this area, that's what would be the distance that the object has covered, or the displacement. So as you can see here, it started out at 5, then after a while it was at 10, goes to a speed of 10, then it goes to a speed of 2, a speed of 15 at time 2. Then after that, at about time 3, the speed hasn't increased, the speed is now falling. The speed is now at almost close to 5. Then a little bit later, at 4 seconds, it's actually stopped moving. It's not moving anymore. What would it mean if I continued this graph all the way down here? This would mean that the car is actually moving backwards. So it's like the car moves, slows down, stops, and then turns around and goes to the opposite direction. So this area here, this area, that is the area that it covers when it's going forward. Maybe it's 10 meters. Let's say it's 10 meters. And then down here, we've also got some area. Down where the graph is below the axis. There's also this space underneath. Well, the car covered, when the car was here in this position, it was in negative velocity, so it wasn't moving in the same direction as this, so it was going backwards, yeah. And so this will also be another distance covered by a car, just in the opposite direction, but we'll look at that a little bit more later. Right now what we're trying to derive is an equation for displacement, velocity, and time. Let's look at that. So we've said that the displacement of the object is the area underneath this velocity time graph. So if we can calculate that area, we would be able to calculate the displacement. So what shape do you see being formed there? Well, it's actually a trapezium. That it's a right angled trapezium. Maybe I should use a slightly different color. There we go. There's our trapezium, and our area is somewhere right there. That's our area right there. Okay, let's calculate the area underneath that. So what's the area of a trapezium? The area of a trapezium is a half times height. A half, the area is a half times the height of the trapezium times the sum of the lengths of the two parallel sides. So the easier thing is always to first identify the two parallel sides. Well, there's this and there's that. Those are the two parallel sides. What does the first parallel side show? Well, it's a 5 here. It's a 5, and then the second parallel side goes from 0 all the way upwards to 15 plus 15. Those are the parallel sides, A and B. And then what's the height of this? The height is the side that meets the parallel sides at a right angle. So this one here, you can see it. There's a right angle there, and there's also another right angle there. So that has to be our height, and that's actually 2. And that's actually time. That's on the time axis. And then we've got a half. So let's derive a formula from these. So the a half, well, that's not changing. That comes from the area of the shape. The half comes from the area of the shape. And what about the 2? What was the 2? Well, the 2 is right there. That's actually time. How long it took for this car to get from a speed of 5 to a speed of 15. So a half times time. That's this all giving us the area underneath that. Brackets. What's the 5? Let's go up and see. 5 is the speed at time 0, or the speed at the start. And the speed at the start, we have a name for that, initial velocity, which we're representing with a u. And then the 15 is actually just the speed at the end of the 2 second time period, which you can see right there. The end of the 2 second time period, it's the speed of 15. So we've got that the area is a half times the time, brackets u plus v. And the area, we've said already that the area underneath this graph represents the displacement of the object. So displacement, let's just write that down. Displacement is equal to a half times time, brackets u plus v, brackets initial velocity times final velocity. Generally, we'll write it down as a half u plus v, brackets time, and this gives us the displacement, which for now I'm representing with a DISP. Now what's important to realize about this is that for this equation only works if we're calculating the area of a trapezium. If we're not calculating the area of a trapezium, we couldn't have used the half height a plus b in the first place, right? We would need to use another formula. So what would we do if we had a curved graph? If we had a curved graph, let's look at that. If we had something that maybe looked like that, or couldn't use the equation for that we've calculated right now, because that's not a trapezium, it's some weird circular shape. We'll need to use something else. We'll need to use actually integration, which is finding the area. That's what we use to find the area underneath a curve. So this formula will only work if your speed is increasing at a constant rate. So you see here, the speed is increasing at a consistent rate. If it's a straight line, where the graph is a straight line, the moment you have a curved line, then it will not work. And actually what we're going to see is that when you have a straight line on the velocity time graph, that tells you that the acceleration is constant. But we will look more at this in the future. So this formula only works when the acceleration is constant. We'll get to it. And it's used to calculate the displacement, a half u plus v, brackets t.